Okay, so we are moving on to kind of the second part of this section. Before we do that, if you were to read through the book and look at what we just talked about, so the first translation theorem, they call this translation on the s-axis, and that's kind of apparent from this this graph right here, where this curve curve for f of s was shifted a units to the left, but we did that by substituting s minus a. So s being the variable, it's shifting along the s-axis, if you think of it in those terms. Now what we're going to be doing is a shift along the t-axis. Remember, when we're using Laplace transforms, we're going back and forth between functions of t and functions of s. And so it kind of makes sense to look at a corresponding shift on the t-axis when we're looking at functions of t. And to help us along in this process, we're going to talk about a function that shows up a lot in math, in engineering, electrical engineering in particular. It shows up a lot. Something that we call the unit step function, or it's also commonly known as the Heaviside function. This is the definition of the unit step function, and there's little modifications that are made to this definition sometimes depending on, what book you're looking at. But essentially it's defined this way. It's a piecewise function that's equal to the constant 0 when t is less than 0, and is equal to the constant 1 when t is greater than or equal to 0. Okay? The usefulness of this function is that it helps us represent kind of a switch. So if you think of like a switch or a signal that can take two states, either on or off, we can interpret 0 as off and 1 as on. So when t is less than 0, the switch is off. When t is greater than or equal to 0, the switch is on. We can use this unit step function to model more complicated piecewise functions. And for our purposes, we need to modify this definition a little bit. So what we're going to do is a couple of things. One, we're going to look at the unit step function, but shifted by a units. And in addition to that, we are going to require t to be non-negative, because again, when we're looking at Laplace transforms and what have you, remember t is always required to be greater than or equal to 0. And so if we were to substitute a t minus a into this function, doing the same for these t's as well, and then solving, we would get that u of t minus a is equal to 0 when t is less than a, and u of t minus a is equal to 1 when t is greater than or equal to a. And then if we also require up here that when this t be greater than or equal to 0 in addition to that, we end up with this definition for our unit step function. Okay, so this is the one we're actually going to be using. I just put this in here because if you were to look up the unit step function or the Heaviside function in a different book or online or something, you might see this definition instead. We're modifying it to make it useful for Laplace transforms, however. Here's the graph of what that would look like. Notice the function is 0 between 0 and a on the t-axis, not including at a, and it's equal to 1 for all values of t greater than or equal to a. So it's got like this broken little piece right here. Okay, now we can use, like I had said before, the unit step function to model just about any piecewise function. Basically, it gives us model is probably the wrong word to use, but an alternative representation for a piecewise function. So to show you how we do that, suppose I have this piecewise function, f of t equals some function g of t when t is between 0 and a, some function h of t when t is greater than or equal to a. We can write this thing using the unit step function like this. F of t is equal to this g of t minus g of t times the unit step function of t minus a, I'm just going to call this u of t minus a, plus this function h of t times u of t minus a. Now, it might not be immediately obvious that these two things are equivalent to each other, but let's think about why this is for a moment. Being a piecewise function, we need to think of this in these two different restrictions on our domain. So when t is between 0 and a, we would like for this thing to equal just g of t. Okay, so let's start by assuming that t is between 0 and a, not including a. Then this would be equal to g of t minus. Now, what can we say about the unit step function, u of t minus a, in this part of our domain? Well, according to our definition, u of t minus a will equal 0 there. So what that means is that both of these terms here will go to 0, leaving me with just f of t minus equals g of t. That's what we want to be happening when t is between 0 and a. What happens when t is greater than or equal to a? Well, in those cases, our unit step function will equal 1. And so plugging a 1 in for the u of t minus a's down here, we would end up with g of t minus g of t, which is 0, plus h of t. So this just becomes f of t equals h of t when t is greater than or equal to a. So this comes out to be the same thing as our piecewise function, but now we can represent it using an alternative notation. This specific type of piecewise function that we're seeing down here shows up frequently as well. Again, think of this as alternating between two states, off and on, where 0 represents off, and now g of t represents on. The reason for the g of t here might be because when our switch is in the on state, we may not want to represent that by a constant function. It may have some kind of changing altitude, something like a sine wave or something. But basically, this function represents the switch being on for a finite amount of time. So our switch will be off where t is between 0 and a, and then when t is greater than or equal to a and less than b, so for this finite interval here, the switch switches on, giving us this function g of t, after which time we switch it back off again. Okay, so these types of piecewise functions show up often enough that we want to do the same thing here. This type of piecewise function, to represent it using a unit step function, would look like this. F of t is equal to g of t, notice that's the only function of t showing up in here, times u of t minus a minus u of t minus b. So these are two different unit step functions, where the a and the b here would be plugged in here in our unit step function. So why is this the same thing as this piecewise function? Well, now we have three different restrictions on our domain to consider. So let's suppose for a second that t is between 0 and a. Specifically, t is less than a. Notice that by the way this is written, it's implied that b is greater than a. So if t is less than a, then it's also less than b, which implies that both of these unit step functions would equal 0. In that case, f of t is equal to g of t times 0 minus 0, which the whole thing would just equal 0. Okay, let's jump down to this step down here. So when t is greater than or equal to b. Again, because b is greater than a, by implication here, if t is greater than or equal to b, then it would also be greater than a. And in that case, both of these unit step functions would equal 1. And so what I have here is g of t times 1 minus 1, which is still 0. So I get a 0 there as well. Going into this middle section here, if t is greater than or equal to a, which is what this part of that inequality is saying, then my unit step function, u of t minus a, will equal 1. But if t is also less than b, then this unit step function will equal 0. And so what I have is g of t times 1 minus 0, or 1, times g of t equals g of t. So this gives me an alternative notation for that. Okay, let's practice converting piecewise functions into this alternative representation. And again, we're basically just going to be plugging things directly into either of these two little formulas based on what kind of a piecewise function we have. So here we have f of t equals t minus 1, where t is between 0 and 4, sine of t, where t is greater than or equal to 4. Okay, so this fits this form, okay, which means I want to plug my g of t and my h of t in to that little formula right there. So let me put that up where we can see it. In this case, f of t would be equal to g of t, which looks like t minus 1, minus g of t again, which is t minus 1, times my unit step function, t minus, now a, where it says t minus a up here, comes from here. Okay, 4 in this case, t minus 4, plus h of t, which is sine of t, times u of t minus 4 again. Okay, and that's it. There's nothing more to it. So really, this is just practicing finding or putting those piecewise functions into that alternative form. All right. Now that we've talked about the definition of that unit step function, we can get into our next translation theorem, our second translation theorem. This one says that if you have a Laplace transform of some function f of t and it's equal to capital F of s, and if a is a positive number, so if a is greater than 0, then excuse me, then we have this formula here, or this translation theorem. So the Laplace transform of little f of t minus a, so notice a substitution has been made in for this t here, times my unit step function of t minus a is equal to e to the negative as times capital F of s. So we're going to prove this one, and then we're going to try an example where we use it. Okay? So again, by the additive interval property of integrals, we can represent this guy as a sum of two integrals. So first of all, what we're looking at here is the Laplace transform of this, f of t minus a times my u of t minus a. And what we're doing is we're going to break this this integral into a sum of two integrals by splitting that interval of integration up using the a that's appearing here. So this thing is the same thing as the integral of that function from 0 to a, plus the integral of that function from a to infinity. And here's where we're going to use the definition of that unit step function. On this interval from 0 to a, we know that our unit step function should be equal to 0 by its definition. So this entire integral here will go straight to 0. When t is greater than or equal to a, which would put us in this interval from a to infinity, that unit step function is equal to 1. So this entire thing simplifies down to this integral right here. The integral from a to infinity of e to the negative st f of t minus a dt. Okay? Now, this looks like a Laplace transform, but it's not exactly the same as a Laplace transform because we need that lower limit of integration to equal 0. And we can obtain that by making a change of variables. So if we define v to equal t minus a, which would make dv equal to dt, and then if we change our limits of integration accordingly, plugging a in for t here gives me v equals a minus a, or 0. Okay, the infinity will remain an infinity. That's easy enough to check. So our limits of integration after making that substitution go to 0 to infinity again. Making the substitution for the t here will give me negative s v plus a. Notice I need to solve that for t. F of v, you can see where the substitution takes place there, dv. Now this does look like a Laplace transform. Okay, and however, we have this translation here, this v plus a appearing right here. And what I can do is distribute my negative s in, and bear in mind that a is a constant, and we're treating s like a constant in this integral. So the e to the negative sa, or the negative as, that will appear here, that whole thing is a constant which can be brought out, leaving me with this, the integral from 0 to infinity, e to the negative sv, f of v dv. This thing in here is exactly the form of a Laplace transform. And if I just change my v's back into t's, just relabel them, then this is the Laplace transform of f of t. So that establishes this theorem. Again, the Laplace transform of f of t minus a times u of t minus a is equal to e to the negative as Laplace of f of t. Okay? Now, in addition to that, we need the ability to find an inverse transform. And so we would just work this backwards. If I take an inverse transform of both sides of this, I'll get that the inverse Laplace transform of this guy, e to the negative as, f of s, is equal to this on the inside, f of t minus a, u of t minus a. And again, it's important to note that this applies when a is positive. Okay, so remember, a needs to be positive in order for this to work. Okay, so I want to evaluate the inverse Laplace transform in this example down here of se to the, actually there's a typo there, that should be a negative st, negative 6t all over s squared plus 16. So what I'm going to do is start by rewriting this in a slightly different form. I'm going to bring my e to the negative 6t s over s squared plus 16. I'm going to bring that e to the negative 6t out like that. Because now this thing here takes on the form of this guy here, okay? And now, to make the connection between what's going on in here and what's going on here, capital F of s is the Laplace transform of f of t, okay? So what we're looking at now is this guy right here as being our capital F of s. Okay, what is the inverse Laplace transform of s over s squared plus 16? Well, this looks like the Laplace transform for cosine, namely s over s squared plus k squared. K would be 4 in this case. So this is the Laplace transform for cosine of 4t. So normally f of t, what we would get by taking an inverse Laplace transform of that guy, would be cosine of 4t. Up here, where do we use this e to the negative 6t? Well, its only purpose is to provide us with the a that's going to appear in our result. In this case, we have negative a, so a would be 6. And that's why I needed to fix that typo right there. Remember, a needs to be a positive number. So 6 is what a is equal to. Now I can plug things into here. So this should be equal to f of t minus a. If this is f of t, then t minus a would look like this. Cosine of 4 times t minus a, and a is 6 in this case. Okay? Times u of t minus 6. Okay? So there we have it. Notice what I needed to do here is put this thing in the correct form. So I brought my e to the negative 6t out so I can more clearly identify what f of s was. Identify the inverse Laplace transform of f of s and call that f of t. Identify my a from here and then plug things into that formula for that inverse transform. Okay? So this is the inverse Laplace transform that we're getting from our second translation theorem. All right. Now, sometimes we have to find the Laplace transform of a function that looks similar to what we got from our second translation theorem, but is not exactly the same. So let me come back to this for a second. This translation theorem is useful for evaluating functions of this form. Some function of t minus a times u of t minus a. Compare that to this. The only difference is that the function in here is not a function of t minus a, it's just a function of t. Can we use the second translation theorem when it doesn't exactly match in that way? And the answer is, of course, yes, otherwise we wouldn't be talking about it. But we need to be careful with how we do it. So what's going to happen here is we're going to make another change of variables. We're going to make a substitution. Suppose I wanted to find the Laplace transform of a function of this type, g of t times my unit step function of t minus a. By definition, that would equal this. Now, again, where are we getting this? Well, normally we would say that the Laplace transform of this guy is equal to the integral from a to infinity from 0 to infinity of e to the negative st times g of t times that unit step function. But like we saw in that previous proof, we can split this up into two integrals, and the integral from 0 to a will have our unit step function equaling 0 there. And that part of the integral will just zero out and go away. Then, using the same idea as that previous proof, we make another change of variables. This time we let u equal t minus a, which again, by changing our limits of integration, this will become 0 to infinity here. Okay? And that is going to give me a new integrand here. It's going to, again, making the substitution for these t's here, I'll get u plus a where I had t's before. Okay, so what does that show us then? Well, once again, if I take that e to the negative s a that I get from distributing the s in here and factor that out of the integral, this integral will reduce down to something of this form, the Laplace transform of g of t plus a. Okay, and again, just like that previous theorem, going straight from this step to this step, it would normally look like g of u plus a, but we're just changing the labels from u's back into t's again, which is totally fine to do. So this gives us a kind of alternative way of dealing with that second translation theorem. Let's do an example. I made a little typo here. I needed to scribble that out. So this should look like the Laplace transform of t times u of t minus 5. Okay, so this takes this form. And in this case, g of t is equal to that guy, t. Okay, according to our translation theorem, or this version of it, this alternative form of our second translation theorem, the Laplace transform of that should equal e to the negative as, where a, remember, is coming from our unit step function right here. A is equal to 5. So this would be equal to, let's write this here, e to the negative 5s times the Laplace transform of g of t plus a, okay, where a, again, is 5. So if g of t equals 5, then g of t plus 5 is literally just t plus 5. Okay? We can, as usual, split that up. This is e to the negative 5s times the Laplace transform of t plus 5 times the Laplace transform of 1, which would equal e to the negative 5s times Laplace transform of t is 1 over s squared. Laplace transform of 1 is 1 over s times 5 would be 5 over s. I don't need a common denominator or anything. I can just leave it like that. Okay? So that's using that other form of that second translation theorem. We have a couple of DEs that we're going to solve. I think I'll do those both in the last video.